good morning or good afternoon or whatever time it is when you are watching this. So today we're going to talk about analysis of variance. Essentially, how do you handle more than one mean or try to model the means of more than one group? So what analysis of variance allows us to do is determine whether or not there are strong differences between the means of at least two groups. If there are, can we find out which groups are different or which specific differences exist? So let's talk about the null and alternative hypothesis for analysis of variance first. So analysis of variance, commonly shortened as ANOVA, which is what I'll refer to it as from here on out, tests the null hypothesis that all K groups have the same population mean. In other words, group 1 is equal to group 2 is equal to group 3, and so on. All of our observations then are assumed to start at the same point. Any difference that we're observing from group to group is just due to random chance. The alternative hypothesis in ANOVA is that there's at least one group that's different from the rest. And when we say different, we mean different in terms of the mean response. So for some I not equal to j, the mu for group I is not the same as the mu for group j. Now, this alternative hypothesis has a limitation. Specifically, it doesn't tell us which group is different, just that some groups are different. Now, we can write this analysis of variance technique as a statistical model, so as a way to describe how each of the observations in our data set were actually generated. So here's what this model looks like. The ANOVA model is y sub ij equal to mu plus alpha I plus epsilon sub ij. The y represents the response variable, so that tells me what I would expect to see, or my response, or my observed value for subject j in group I. We're assuming that each of these observations can be written in three parts. So we have a mean for each group, or we have an overall mean, a grand mean mu. We have a group effect for group I, alpha I, and then we have some error term representing the individual variability from group to group. Each group then has its own average. We call that mu sub I. That's equal to the overall mean, or the grand mean mu, plus the group effect. So let's look at a data set to see how this all plays together. So we've got a data set here with 12 observations split into three groups. So 4 observations in group A, 4 in group B, and 4 in group C. Here I've plotted bars for each of these individual observations, just so we can see how they compare. So group A tends to be smaller, group B is kind of in the middle, group C tends to have higher observations. So the first thing we'll do with this ANOVA model is try to think about what the overall mean, or the grand mean mu, is going to look like. This is our best guess for the overall population mean. So I'm just going to take the average of all 12 observations to give me that grand mean mu. So our overall average is 11.6, roughly. Here I've drawn a line over that 11.6. Group A tends to be a bit lower. Group B falls pretty close in line with the mean. Group C is a bit bigger. We need a good way to measure how far or how different each of these groups is from the mean, and then an overall measure of variability. So the next thing we're going to try to do is find the group effects, and that will tell us how far on average the groups are from the mean. So to get the group effects, I'm going to take the average of each group. So the average of group A is 7.75. Average of group B is 11.5. Average of group C is 15.5. And then I'll take the difference of those compared to the overall mean. So group A has a negative group effect. So A is 3.83 units below the overall mean. Group B is also below the overall mean, but not much. Group C, this should say above the mean. So some groups will be below average, some groups will be above average. So here's how all of those groups come together. I've then added these red lines representing the distance from the mean. Group A is below average, Group B is just about average. Group C is above average. The last part of this ANOVA model are the errors. So what we'd like to do is for each observation, count up how far they are from their group mean. Now, which of these is explaining more of the variability in this data? Are we explaining more of it by comparing the groups? Or is there more variation in these error terms? That's the question that ANOVA really tries to answer. To fit or calculate the ANOVA model in R, we'll use a function called AOV, that stands for analysis of variance. We'll see how our response variable Y changes depending on group. The data set is just simply called data here. We then get what's called the ANOVA table. We'll go through each of the pieces of this. What we want to look for here is the p-value. There is a strong p-value, so it looks like splitting the data up into groups is explaining the variability. We will reject then our null hypothesis based on a p-value that small. In other words, there's some pretty strong evidence to show that the mean of at least one group is different from the mean of the other groups. There are some assumptions with this model. Here are those three assumptions. There's some parameters to this model. There's a population mean mu. There is a group effect, alpha. There's also something called sigma squared. So sigma squared is a measure of the error variance. These are all constant parameters. In other words, we don't know what values they take on, but they're not going to change. Our second assumption is that the ANOVA model is additive. So we're just adding group effects to the overall mean. We're not multiplying anything. We're not raising anything to a power. Our third assumption is that these error terms are independent and identically distributed, so they're not related, the variability from one to the other. We're also then assuming that they're following a normal model, then with mean zero. In other words, the errors should really just average out. Here's the last assumption. The population variances for each group have to be equal. In other words, what that means is that the groups should have roughly the same standard deviation or variability. So let's take a look at an example. We're going to take a look at some data from a study of tooth etching time on resin bonding strength. So looking at how long we need to etch a tooth or leave some chemical gel on the tooth to etch it before applying a bond. Our data comes from a sample of 78 undamaged, recently extracted first molars or baby teeth. We randomly assigned each of these baby teeth to receive a phosphoric acid gel etching for either 15, 30, or 60 seconds. The researchers then looked at how much force was needed to break that bond after 24 hours. So we'll first write the ANOVA null and alternative hypotheses. We have three treatment groups, 15 seconds, 30 seconds, or 60 seconds. So those are the three groups we'd like to compare. Our null hypothesis is that the mean is the same for all three groups. Our alternative is that the mean failure load is different for at least one group compared to the rest. Now, looking at this data, it looks like there are going to be some differences. The bonds that in general had lower etching time looked weaker. There may be some difference in variability. The 15-second group has a smaller standard deviation than the 60-second group. To estimate these group effects, we need the averages for each group and the overall mean. Here I've chosen to use the summarize function just because the output's a little bit smaller. So our estimate, or our best guess for the overall grand mean, is just the sample average, so 6.41. Each group effect measures how far we are from the overall average. So the 15-second group is a little bit below average. They have a negative group effect. The 30-second group is a little bit below average as well, so they have a negative group effect. The 60-second, or the longest group, is a little bit above average. They have a positive group effect. If you add these three group effects together, you should get zero. In other words, the groups eventually sort of cancel each other out. Now, in order to finish out this hypothesis test, we need a test statistic and a p-value. The test statistic that we're going to use here is something called an F statistic. The F statistic is a ratio of two measures of variability. We calculate something called mean squared group, or MS group. That measures how different each of the group levels are, whereas MS error measures the variability of those error terms, so within each group. Now, if these groups all have the same mean, here's what we would expect. We would then expect this MS group, the levels of each factor should be similar, so there shouldn't be a lot of variability. MS group should be small, the F statistic should be small. So large values of that F statistic are going to indicate that the groups are themselves different. Now, anytime you fit this ANOVA model in software like R, you'll get the results in an ANOVA table. The table looks like this. The calculation details are in your textbook. What I'd like to do is just highlight the important features of this table. Here's the first useful feature, the degrees of freedom column, or the DF column. I like to use the values in this as sort of a sanity check. N is the sample size, K is the number of groups. So this degrees of freedom for groups should be K minus 1. If it's not, that's usually a good indication that something's gone wrong with how your model's being fit. If this total isn't N minus 1, there's usually a good indication that something's up with your model. The test statistic is reported in this F column, so that's the F statistic, and then the p-value is reported in the p-value column. So here's what this ANOVA model looks like. We'll see how failure load depends on etch time. So we write failure load tilde etching time. Data is the tooth etch data set. Here's a summary. We have three groups, so our degrees of freedom here should be 3 minus 1 or 2, so that's good. That's a good check. Our F value, our measure of variation, is 8. This is pretty high. Here's our p-value, 0.0003. So based on this, we'll reject the null hypothesis. There's some pretty strong evidence to show the failure load is different for at least one of the etching times. Sorry, my son is being a dinosaur upstairs. So that's called the one-way ANOVA model, and it's called the one-way model because there's just a single explanatory variable. Now, factorial experiments introduce a second explanatory variable. The model doesn't change all that much, so the two-way ANOVA model just adds a second factor. So we have an effect of factor A, so we have group effects for A, and we have group effects for B. So we're just adding another variable to this. When we fit a two-way ANOVA model, we're actually testing two null hypotheses simultaneously. So our first null hypothesis is that the group effects are all the same for factor A. Our second null hypothesis is that the group effects are all the same for factor B. The alternatives are that at least one level is different for A or B. The two-way ANOVA table then has two rows. We've got a row for factor A and a row for factor B. In the degrees of freedom, these indicate the number of categories. So we should have A minus 1, so the number of categories for variable A minus 1, number of categories for variable B minus 1. So let's take a look at a new example. We're going to take a look at an example or an experiment that was done to measure oxygen inhibition. So the researchers wanted to compare the effect of oxygen on the metabolism of two different sugars, glucose and galactose, by strep. We've got 4 levels of oxygen. So this means that we've got essentially 2 explanatory variables. We've got sugar and the oxygen concentration. So sugar is our first explanatory variable. Oxygen concentration is our second explanatory variable. The amount of ethanol that's produced is our response variable. So here's our two-way ANOVA model. We now have 2 variables, A and B. So factor A, sugar, we're assuming that glucose and galactose are equal. Factor B, oxygen concentration, there were 4 levels of that. So we're assuming that the 4 effects on ethanol are the same. Now, there's something wrong with this ANOVA table. It's not the code, so this is correct. We'll fit this model just by adding additional explanatory variables with a plus sign. So we've got sugar plus oxygen concentration. Oxygen concentration had 4 levels, so it should have 4 minus 1, 3 degrees of freedom. What happened here was that oxygen concentration has numerical variables. So R assumed we want to treat it like a numerical variable. The solution, which you may have to do on your projects or your homeworks, is to reclassify ethanol as a factor. So tell R that no, these are categories, not numbers. Once we do this, we refit the model, get the correct degrees of freedom. So that's why I always like to check my degrees of freedom first. And here's the conclusion. Sugar, it looks like, has a strong effect on ethanol levels. The sugar p-value is quite small. Oxygen concentration might have some effect. The p-value is about 0.06, so it's not strong, compelling evidence, but there may be some evidence. Now, once the model's been fit, there's a really helpful function in R called model.tables that we can use to help estimate the overall group mean and effects. So you can feed in your model that you fit, ask to calculate the means, and they're spit back out. So we've got the overall average ethanol, which is 17. Glucose looks like it's much higher than galactose. It also looks like as we increase the oxygen concentration, we're decreasing the amount of ethanol that's produced. Now here's the question that we need to answer. With glucose and galactose, it's pretty easy to tell that these two are going to be different. But with oxygen concentration, which pairs are different? Is 0 different from 46? Is 0 different from 92? Is 0 different from 138? We don't know yet. The method that we're going to use to find out is something called Tukey's honest significant differences. So Tukey's honest significant differences, or Tukey's HSD, can be used to compare more than one pair of groups. This matters because when we do ANOVA, we end up in a situation where multiple comparisons become a problem. The idea behind this multiple comparison problem is really simple. The more tests we do, the more likely that at least one of those tests result in an error. Tukey's HSD adjusts for that automatically. In order to implement this adjustment, all we need to do is use the R function Tukey HSD. I'm going to input my model, so here's results.ethanol. What this will do for me is automatically calculate both confidence intervals and a p-value for a pairwise comparison of the groups. So for example, if I want to know how glucose and galactose compare, I have the difference between the two groups, the lower value of a confidence interval for their difference, the upper value of a confidence interval for their difference, and a p-value. So yes, this is a significant difference between glucose and galactose. For oxygen concentration, same thing. We've got difference, confidence intervals, and adjusted p-values. So it looks like the groups that are different in terms of oxygen concentration, there's a difference between the highest oxygen concentration and the lowest oxygen concentration. The others aren't that different. You can then plot these if you want to see how these confidence intervals compare. So we have differences in mean sugar levels, differences in mean oxygen concentration levels. This dotted line will always be drawn at 0. So if the difference could plausibly be 0, the two groups are effectively the same. We can use this for our one-way ANOVA model as well. So going back to the tooth etching time example, it looked like there were some pretty strong differences in that bond strength. Looking at this output, The strongest difference is between the 60-second etch time and the 50-second etch time. 60 and 30 seconds is kind of different. 30 and 15 is kind of different, but really it's 60 versus 15 where the difference is the strongest. So that covers analysis of variance. You'll get some practice with these concepts on the practice quiz and the homework. Next week, we'll talk about correlation. Have a great day.